In this video, we're actually going to go ahead and start simplifying radical expressions. These are going to be more advanced radical expressions. We're not going to actually start with the advanced ones, but we'll build into them. A couple prerequisites here. You have to know pretty much everything about exponents, the laws of exponents, that type of thing, negative exponents and rational exponents. You should also be very familiar with radicals, how to take square roots, cube roots, fourth roots, business like that. Also, there's a subtle prerequisite here, one for the concepts. I will talk a little bit about them, only to show them, but I have a previous video for that, seeing the concepts of simplifying radical expressions. Specifically, stuff like the fact that you can split multiplication when it occurs underneath a radical. So like the nth root of a times b is just the nth root of a times the nth root of b, for a and b being positive or zero. There's a lot more to this, so please watch the concept video for a long discussion on this. Also, you can split division. So the nth root of the fraction a over b is the nth root of a over the nth root of b. Again, where a and b are positive or a can be zero. And again, I'll repeat my warning that you cannot split a radical if there's addition or subtraction inside. And again, this is from the concept video, so please watch that. And finally, the definition of a simplified radical expression. So a radical expression is said to be simplified if it matches all four of these conditions. And as you probably noticed from the conceptual video that you've already watched, I'm sure, is that I don't really focus too much on the fact that all denominators have to be rationalized in order for it to be considered simplified. It's a kind of a throwback to history there. But the first, second, and the fourth are very important. The third is just dependent upon your instructor. So each factor in the radicand has to be to a power that's less than the index of the radical. The radicand contains no fractions or negative numbers. And finally, each term contains only one radical. Each time that I do a problem for simplification, I will reference this definition. So let's go ahead and start with the negative fourth root of 729. Following the order of operations, I look on the inside of that radical and see if I can simplify 729, which I cannot. So then I reach to the radical itself, the fourth root, and you start trying to manipulate that radical. Can you break apart 729 into the product of two numbers of which you could take the fourth root of at least one of them? So let's put the fourth root here. One thing I like to do if I'm doing a problem is I'll make out a list, like a list of x and then x to the fourth. In this case, because I'm dealing with the fourth root. And I'll say, well, 2 and 2 to the fourth is 16, and 3 to the fourth is 9 times 9, which is 81. And then 4 to the fourth is 16 times 16, which is 256. And 5 to the fourth is 25 times 25, which is 625, and so on and so forth. By the way, it might be helpful for this problem to also write out 6 to the fourth. So we have 6, and 6 to the fourth is going to be 1,296. The reason why I want to write that one out is because we know we're not looking for the fourth. Our answer is not going to involve a 6, because the fact is 729 is too small, right? We don't have enough power to take the fourth root of to get a 6 out of the answer. So then I start looking through these numbers and saying, does 16 divide into 729? Well, it doesn't, because 729 would have to be even. But 81 might. If you grab a calculator and you just type in 729 divided by 81, you'll find out that 81 actually does go into 729 9 times. So now I'm going to use this idea, this theorem that we introduced in the past, this one right here, that if we have the product of two numbers, we can break apart that radical into the product of two radicals. So let's go ahead and use this property here. Go back to the example. We're going to split the product up. Oops, I already have an equal sign in there. So notice the radical has a negative in front of it. We still aren't messing with that negative. The negative's still there. It's just going to be the fourth root of the first factor times the fourth root of the second factor. And from this list over here, I know the fourth root of 81 is going to be 3. The fourth root of 9. And from this point forward, I'm just going to check to see if this is as simplified as it gets. Well, I have the fourth root of 9. The fourth root of 9, well, that actually doesn't simplify down any further. I can't break 9 apart into two numbers, one of which I could take the fourth root of. So that's kind of as good as it gets. This is a simplified version of the negative fourth root of 729. So negative 3 times the fourth root of 9. By the way, when you're writing these out, make sure that you put your index on the radical. Try to kind of scoot it over to the right a little bit, because otherwise it'll start looking like 3 to the fourth power to you. So be careful about that. All right, let's try another example here. Oh, and you know what? Actually, before I do my next example, I want to mention one last thing here. We could, and it's always a great idea, I just avoid doing it sometimes, we could talk about what 9 is in terms of powers of primes. So in other words, if you think about it, 9 is just 3 squared, isn't it? If you think about it this way, then you could change this radical notation into rational exponent notation. Now recall, rational exponent notation goes like this. It's 3 to the, well, the power is 2, and the root is 4. So you do it, the power goes on top, and the root of the radical, or the index of the radical, goes in the denominator. And you see that fraction will actually simplify. So this will be negative 3 times 3 to the 1/2. And then I could rewrite this answer as a final radical. This would be negative 3 times the square root of 3. So this technically is the most simplified version of that answer. I almost didn't see that. There is a way to guarantee that you can see it. I should probably do this a second way. Or maybe I shouldn't say a second way, but just maybe I should reinforce the way we did this. So often, okay, we have the radical or the root of some constant. What I generally do is try to break apart that constant into the product of two numbers, one of which I could take the fourth root of, or the fifth root, whatever root we're talking. And then I break that apart. I can split radicals amongst multiplication here. And then I go ahead and apply the fourth root to the perfect fourth power to kind of simplify that down. Once I get that answer, here I am at this step, I then usually check at this step to see if it simplifies any further. And the way you could do this is check this by writing with rational exponent notation, and then completely factoring the radicand. So if you notice, that's what I did. I completely factored the radicand. That's this bit right here. I completely factored it to 3 times 3, or 3 squared. And then I wrote it in rational exponent notation in the next step. I simplified that rational exponent notation, and then I finally rewrote it in radical notation in simplified form. So that's the basic way. Now, a lot of people are going to try to memorize this. I wouldn't try to memorize this. Well, I mean, I suppose you're going to have to. But the basic process is pretty straightforward to split the radical and take the fourth root. It's just from this point right here, that's the part where a lot of people will fall apart. So just remember, check to see if you can simplify this radical any further by seeing if 9 can be written as something squared, and maybe things will cancel out nicely. This definitely calls for another example. Let's take a look at the third root of 128 times b to the 11th. Now, when I see the third root, I immediately think, okay, you know what, I better list out some third powers. So, or I'm sorry, that shouldn't be n, x to the third. So let's see, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, and I know that 6 to the third is going to be over 128, so I'm not going to bother with it. Okay, so now what I'm going to initially do, and I always recommend this, and maybe I'll write this down below here, because I noticed some of my videos break the top of my handwriting there. What I'm going to do is break this into the cubed root of 128 times the cubed root of b to the 11th. That's the first thing I usually do, so I can work on the numerical radical first. And let's see, can 125 go in 128? No. I usually start, by the way, with the largest. Can 64 go into 128? Yes, 64 can. So this will be the cubed root of 64 times 2, actually, and times the cubed root of b to the 11th. Now I'll show you kind of a trick with that cube root of b to 11th in a moment, but let's take care of this cube root of 64. So I'm going to split that into the cube root of 64 times the cubed root of 2 times, again, the cubed root of b to the 11th. This is definitely not simplified because, look, this expression here only has one term. There's no addition or subtraction going on. But there's a ton of radicals. That's a completely illegal thing to leave as a final answer. So just to let you know, this is not simplified. The third root of 64, as we see from this table over here, is going to be 4. So we'll have 4 times the third root of 2 times the third root of b to the 11th. Now let me just show you how a textbook usually handles that third root of b to the 11th, and then I'll show you how I handle the third root of b to the 11th. The third root of b to the 11th via a textbook looks like this. Oh, that's like the cube root of b cubed times b cubed times b cubed times b squared. It actually is. If you add up those exponents, 3 plus 3 plus 3 plus 2 is 11. And then it breaks it apart and says, oh, look, that's the cube root of b cubed times, you get the point, right? Cube root of b cubed. A little extra work here. Times the cube root of b cubed. This is why I never teach it this way. Times the cube root of b squared. And of course, the cube root of b cubed, well, that's kind of nice. We have a theorem concerning that. Let me go ahead and show you. The nth root of b to the nth power is equal to b as long as b is positive or 0. There's more to this theorem we'll discuss later, but this is basically it, that the nth root undoes the nth power. As long as your base is positive, and we made one assumption with this problem. We are assuming all variables represent positive numbers. So for now, let's just assume that the nth root, or in this case the third root of b to the third, will just turn into b. They undo each other. So it's going to be b, next one will be a b, the next one will be a b, and the last one actually doesn't simplify down. It's just cube root of b squared. B times b times b is b cubed times the cubed root of b squared. Oh, and la-di-da-di, we get this business. Oh, that's equal to the fourth root of the cubed root of 2 times b to the third power times the cubed root of b squared. Now, before I simplify this any further, which it does, but I want to talk to you about this, that's using the textbook's method. Textbook's method, again, just splits this into powers of 3, the same power as the index, and you have some remaining power here. We'll call that the remainder power for a reason in a moment. And then you can break up those radicals to the cube root of b cubed, cube root of b cubed, cube root of b cubed, and the cube root of b squared. And of course, cube roots undo cubes, so those two will undo each other. You'll just get b times b times b, and then the cube root of b squared, b cubed, cube root of b squared. That's, again, the way a book would do it. Here's how I would do it. We have the cube root of b to the 11th power. In rational exponent notation, that's b to the, well, the power goes up top, the index of the radicand, or the radical, goes on the bottom. So b to the 11 thirds power. Oh, well, I wonder if I could write that as a mixed number, maybe. This is one of the only uses of mixed numbers in mathematics. How many times does 3 go into 11? Well, that would be 3 times. And, let me put plus, with what remainder? Well, 2. So, that's b to the 3 and 2/3, or b to the 3 plus 2/3, says the same thing. And of course, I could break that apart to be b cubed times b to the 2/3. But this last bit I can write in radical notation as b cubed times, well, that's going to be the index of the radical is going to be the denominator, so that's the cube root. B to the, and the numerator of the rational exponent is going to be the power. And notice that's the same as this answer right here. Same exact answer. That's how I generally do it when I have variables underneath a radical. So I use rational exponent notation. When you start working with this enough, you'll do it quickly to where you just say, well, how many times does 3 go in 11? Oh, it goes in 3 times, so it'll be the third, and with remainder 2 on the inside. But I don't expect you to be able to do that right now. All right, we're not done with this example because radicals we like to write at the back end of a term. So I'll write the 4 out front and then the b to the third times, and then we have the cube root of 2 times the cube root of b squared. But again, this is not simplified because remember, the definition of simplified says that each term contains only one radical. In other words, business like this is not allowed. We have 2 cube roots there, that's not allowed. And same thing with what we're working with. This 2 cube root business, not allowed. But they're the same index on the radicals, so we can combine them. There'll be 4b cubed times the cubed root, since they're the same index, of 2b squared. That's done. That is completely simplified. That will be our answer. Seems like a lot of work to these actually, but it's not once you get used to them. You just start kind of cruising through them, but it takes a little bit to get used to the work. Now this example is going to be an odd example for most people, I think, because in general, I'm going to be going against the order of operations here. The only reason why is because it makes the math a little bit faster and easier to do. So this is what I recommend doing. If you have a fraction that's been given to you that has radicals in both the numerator and the denominator, and if there's no addition or subtraction going on, then I would glue them together as one radical first. So I'd call this the cube root of 8b to the 7th over a to the 6th b to the 2nd. You can do that as long as the radicals have the same index and there's no addition or subtraction going on the outside of the radicals. So this is just using the following theorem, this theorem right here, where if you have a radical over a radical and they have the same index, you can glue them together. All right, so going back. Now what I'll do is I'll work inside this radical to simplify things down. So I'm working inside the cube root here, and I'll look through these and say, can anything cancel? Well, I can easily see that I have b to the 7th up top, b squared downstairs. Who wins by how much? Well, the top wins by 5. And I still have a to the 6th downstairs. Once I see the fractions completely simplified, which it is, then I'll re-break it. So that'll be the cube root of 8b to the 5th over the cube root of a to the 6th. I promise you'll save yourself a headache if you just glue them, if you follow this method where you glue the radicals together first to simplify and then re-break them. Now I happen to know what the cube root of 8 is, and we'll use my little trick for the cube root of b to the 5th. Downstairs we have the cube root of a to the 6th, which I'll also use my trick for. Now remember, when doing these problems, I had told you earlier, you must assume that all variables represent positive numbers. Okay? I just have to reiterate that here. All right. So going back into this example, I see this is equal to the cube root of 8 is just 2. And I'm going to rewrite this second factor up top as a rational exponent, so b to the 5/3. It's often much easier to do that. Downstairs I'll do the same thing, a to the 6/3. I'll simplify these rational exponents, so I have 2 times, let's see, I'll write that as a mixed number. B to the, well, 3 goes into 5 once with a remainder of 2. And then downstairs, 3 goes into 6 twice. So this is going to be 2b to the first times b to the 2/3 over a to the second. Or in other words, 2b times the cubed root of b squared over a squared. Notice that in this case, this is completely simplified because, one, you don't have radical times radical upstairs, just one radical. Same thing downstairs. The power on the stuff inside the radical, basically the radicand, is less than the index. Great. And also we don't have any negative numbers inside the radical, nor do we have any fractions inside the radical. So this is completely simplified. This is the final answer. In this next example, we'll take a look at the cube root of 2a squared times the cube root of 6a squared. And we're going to do the same thing we did in the last example. Instead of working on the inside of these radicals first, we're going to combine them. So this is the only break that I know of offhand in the order of operations. Normally with the order of operations, you would work on the inside and clean it up as much as possible, and then try to take the cube roots. But generally with radicals like this, you're going to end up doing kind of a weird combination of them first. So in other words, whenever you're multiplying radicals or dividing radicals, try to combine them up if they have the same index. So in this case, we'll have the cubed root of 2a squared times 6a being squared. And that'll equal the cubed root of 12a to the 4th. And now you start looking at cubed roots here. So I'll make a table of inputs, and then the outputs will be their cubes actually. So we have like 2 cubed is 8, and we have 3 cubed is 27. Well, all of a sudden I see 27 is much larger than 12, so that's not going to work out for us. So now I know that there's no way I can reduce that 12 there. The cube root of 12 is just the cube root of 12. It can't be reduced at all. However, that cubed root of a to the 4th can be reduced. So let's just take our time with it at first, and then I'll show you kind of a speedy way to do it. It's the cube root of 12 times the cubed root of a to the 4th. I could do this for a couple reasons. One, because we know that the radical of the product of two numbers is the same thing as the radical of the first number times the radical of the second number, as long as both numbers are positive. So that's the second reason. Both numbers are positive here. Okay, now we know the cube root of 12 doesn't simplify. However, let's go ahead and rewrite that second cube root as a rational exponent. So that'll be a to the power 4 over the root 3. And this actually will reduce down. So that'll be the cube root of 12 times a to the first times a to the 1/3. See how quickly I did that? And now you have three objects multiplying. I can order them any which way I want. I will do the stuff without the radical signs. I'll pull those out front. So I'll put a times the cube root of 12, and then a to the 1/3 is the same thing as the cube root of a. And this is not simplified yet because these two cube roots have to be combined. So you recombine those. That'll be a times the cube root of 12a. Now let me just show you as an aside here, had we just done the following, after a while you just get fast enough that you'll do it this way. You'll say, okay, I can't take the cube root of 12, so that's going to stick in there. But 3 goes into 4 once, with remainder 1. Let me write down what I said there. 3 goes into 4 once with a remainder of 1. I should color code this. So hopefully you can read my changing colors here. 3 in black there goes into the 4, which is in red there, once. So the number of times it goes in is the power on the outside there. And then with remainder in gray of 1. So the remainder power goes on the inside. Okay. So I'll use both these methods throughout the rest of the example so that you can see how speedy that method is. Because notice that really doing that kind of skipped a lot, well, 1, 2, 3, 4 extra steps. So we just ended up with a times the cube root of 12a really quickly. Now this next example is not as simple as the last few. It's simple in a way, but it has some extra little work associated with it. First thing I want to tell you is we do not have any type of rule that says like the square root of a plus the square root of b is equal to the square root of a plus b. That's not true. We have nothing that tells us that's true. So you can never use that. I often like to say whatever you want to be true with addition or subtraction just isn't. So we'll actually start this example by simplifying each of these terms first. So each term we're going to zoom in on. Now I'm looking at the square root and I'm thinking, okay, maybe because I can't take the square root of 50, maybe I could break it into two numbers, one of which I can take the square root of, and I see that I can break it into 25 and 2. And at 32, the same thing, I cannot take the square root of 32. However, I can break it into 16 and 2, and 16 I could definitely take the square root of. So let's pull these apart. We can do that. That'll be the square root of 25 times the square root of 2x plus the square root of 16 times the square root of 2x. When you're writing this down, by the way, for an instructor, make sure that you keep the radical sign going as far as you can here until you're sure that it looks like it's covering both the 2 and the x. It's very important. Alright, so square root of 25 is just 5 times square root of 2x plus square root of 16 is 4 times the square root of 2x. And now you ask yourself if there's anything else you can do. And this just gets back down to that old method of combining like terms. There's a couple ways you can view it. When I teach it in class, I use a very kind of demeaning method, or not demeaning, I guess, but very basic method where I say, listen, whatever's after the coefficient is a picture. That's all this is. That's just a picture. I have 5 of those pictures. And then I have 4 of these pictures over here. Are they the same pictures? That's all I'm asking. Are those 2 pictures exactly the same? If they are, then you can add them up. I have 5 of them here, plus another 4 of them there. So altogether, I have 9 of them. Okay. I guess that wasn't too childish to teach it that way. Alright, so that's an example of adding with radicals, or adding radical expressions. The idea is to simplify each of them, and if they have something in common, go ahead and add those up. Or if they have everything in common. So let's try another one of these problems, but with some subtraction in here. I see a bunch of cube roots, so I'm just going to go ahead and write out a few cubes. So like 2 being cubed is 8, 3 being cubed is 27, and 4 being cubed is 64. And really I don't need to go I didn't even need to go to 64 because the fact is that's larger than any of these cube roots. Okay. So let's see. I don't see an 8, a 27, or a 64 in any of these radicands at first. They're not explicitly written that way. However, I know that 16 can be written as 8 times 2. 2, you're kind of stuck here. That's just going to be the cube root of 2. And then 54, let's see, is it divisible by 8? No, it's not. Is it divisible by 27? Yes, it is. That's 27 times 2. So let's write that in there. And now remember, radicals of products can be split apart. So let's say that's the cube root of 8 times the cube root of 2. And again, when you've done enough of these, you don't have to take your time with these. I'm taking my time just so that I can show every single step, so that, I don't know who's watching this. Somebody might be watching and going, I totally don't understand what's going on. Who knows? So I break each of those apart, and then I take the cube roots of the stuff that I can. It's going to be 3 times 2 times the cubed root of 2 minus the cubed root of 2 minus 2 times 3 times the cubed root of 2. So that'll be 6 times the cubed root of 2 minus the cubed root of 2 minus 6 times the cubed root of 2. And now you ask yourself if you can simplify these any further. Each term you cannot. However, you then ask yourself, do they all have the same pictures? Well, I have 6 of these pictures right here. I have a -1 of the same pictures, actually, right there. And then I'm losing 6 more of the same pictures. So I have 6 of them, -1 minus another 6. That'll give me a -1 of those pictures altogether. So I'll have a -1 of those pictures. By the way, -1 is the same thing as saying just negative of those pictures. For the last 3 examples in this lecture, we're going to spend time just expanding radical expressions. And this works, the only reason I'm doing this is I want to convince you that this works just like it would work if these were regular old numbers. Well, sort of. I mean, you can't, if they were regular numbers, you would be able to add that 6 and 10, but because they're radicals, you can't add them. They're not like terms. But the idea is still the same. You can distribute. So we'll go ahead and distribute the square root of 2 to the square root of 6 and the square root of 10. Let me show you that action by circling up the square root of 2 here. And I'm going to attach it to the square root of 6 and the square root of 10. This will be square root of 2 times the square root of 6 plus the square root of 2 times the square root of 10. And of course, each of these can be combined. So it'll be the square root of 12 plus the square root of 20. And now, once you reach this point, you want to simplify each radical. So let's see if we can do this. The square root of 12, I know 12 can be written as 4 times 3. 20 can be written as 4 times 5. So square root of 4 will give me 2 of those root 3's, plus square root of 4 will give me 2 of those root 5's. And then you ask yourself, are these like terms? Well, I have 2 of these pictures, and I have 5 of these completely different pictures, completely different terms. They cannot be, I'm sorry, you have 2 of those completely different pictures there, and they cannot be combined because they're completely different pictures. So you're pretty much stuck. This is as good as it gets. And that's often the case when you're expanding or multiplying radical expressions, is that a lot of stuff does not combine. Some things do, but not a lot. So let's try our hand at this again. We have the cube root of 2 times the quantity, cube root of 20 minus 2 times the cube root of 12. Just to make sure you understand, we're not going to simplify the radicals first. We'll save simplifying radicals to the very end. It just kind of helps out to wait. But if you like to simplify first, more power to you. It's not going to make you wrong or anything. It's just, I think you'll end up realizing after a while that you're simplifying twice in the long run. So, or you can. In this case, you don't have to, but in a lot of cases, you will be simplifying twice if you simplify at the beginning and then at the end as well. So let's distribute this cube root of 2 to each of the terms inside the parentheses. And to do that, we'll have the cube root of 2 times the cube root of 20 minus 2 times the cube root of 2 times the cube root of 12. Notice that when I did this on the second term, when I multiplied the cube root of 2 times the second term, I reordered the multiplication to have the coefficient out front, that 2 out front. That's a good habit to get into. Alright, let's see what happens here. We get the cube root of 2 times 20, or in other words, the cube root of 40. minus 2 times the cube root of 2 times 12, or 24. Now again, I'll list out really quickly. You don't obviously have to do it once you know your numbers, but 2 and 2 cubed is 8, and 3 and 3 cubed is 27. I'm not going to go any further. Let's see if 8 divides into either of these, and you see that actually 40 is divisible by 8. That's the cube root of 8 times 5 minus 2 times the cube root, and this is also divisible by 8. That's 8 times 3. Cube root of 8 is 2 times the cube root of 5. By the way, a mistake I often see is that students will forget to write the index of 3. They start writing square roots after a while. That cube root will always stay in the problem unless you simplify it out, but it's rare that it gets simplified out. Okay. Anyway, minus 2 times, let's see, the cube root of 8 is 2, and then we're left with the cube root of 3 on the inside. And one last little cleanup here. This is 2 times the cube root of 5 minus 4 times the cube root of 3. And again, I ask myself, what are the pictures? I have 2 of these pictures here. And then I have a negative 4 of these pictures. And notice they're not the same exact picture. So they cannot be combined. You're just stuck. Great way to do it. If you have a highlighter, that's a perfect way to do a problem, because it really does. If you highlight like terms with, or basically the same pictures with the same highlighter color, it really does make things jump out at you that they can combine or they cannot combine. Now we're down to the final example in this lecture, and this is one of my favorite examples to give just because I find that a lot of students still don't understand that this is the square root of 5 minus the square root of 2 times the square root of 5 minus the square root of 2. So I just want to start by saying this is not equal to the square root of 5 squared minus or plus, I don't really care what you think it is, the square root of 2 being squared. It's not equal to that. Remember, we cannot apply a power to each term in a parentheses. You can apply a power to each factor as long as there's no addition or subtraction. So addition and subtraction really do mess everything up. You cannot do whatever you want to do with them. They're the 2 worst operations in the world. So let's see what happens here. This is actually going to be the square root of 5 minus the square root of 2 times the square root of 5 minus the square root of 2. And now I'm just going to use plain old distribution like we did in the olden days. So square root of 5 times the square root of 5, square root of 5 times the negative square root of 2, and then negative square root of 2 times the square root of 5, and negative square root of 2 times the negative square root of 2. Here we go. I'll just write that out. Root 5 times root 5, and then apply the root 5 to the negative root 2, so I'll get a negative root 5 times the root 2. That's the stuff in blue. And in black, I should have written that in black, minus root 2, root 5, and then negative root 2 times the negative root 2 is a positive root 2, root 2. Now we just clean this up. Root 5 times root 5 is square root of 25, minus the square root of 10, minus the square root of 10, plus square root of 4. And this does simplify quite a bit. That's going to be 5. Let's see. I have a negative one of these pictures and another one of these pictures being lost right here. So I'm losing 2 of them altogether. And finally, plus 2. We're not done here because 5 plus 2 is just 7. And then you want to make sure that that square root of 10 is simplified, but it actually is. There's no way I can break that up. It only breaks into 2 and 5, so nothing that I can take the square root of there. And this is completely done. Now, a couple things you should note here that I want you to start getting used to is that the square root of 5 times the square root of 5 is equal to 5, and the square root of 2 times the square root of 2 is equal to 2. Here's how I used to think about it when I was a student. And by the way, this should be pretty obvious, but here's a great way to think about it anyway. The square root is really saying the half power, right? Because the square root of 5 is the same thing as saying 5 to the 1 half. That's the root is in the denominator and the power on 5 is on top, so that's the square root of 5 to the first. So I'm saying I have a half power of 5 and I'm gluing onto it another half power of 5. I should end up with a full power of 5. That's really what I think about when I see two numbers being multiplied, two square roots being multiplied that have the same radicand. I go, well, I have a half power of 5 times a half power of 5. I have a full power of 5. Same thing with 2 square root of 2. That's 2 to the 1 half times 2 to the 1 half. Half power 2 times a half power of 2 should be a full power of 2. So that's generally how I've always thought of it, and I think it's a great way to think about square roots, is that they're half powers. They're not a full power, they're a half power. All right. Okay, so that does it for simplifying radicals, at least right now. In the next lecture, we'll take on a brief, what I consider advanced topic in simplification of radicals. It's just kind of a side topic in simplification of radicals. And then we'll do some rationalizing of denominators in a future lecture. And finally, for radicals, we'll talk about simplifying some weird radical things when we do not, radical expressions that is, when we do not assume that variables are positive. So we'll see what happens when variables are negative.